Good afternoon, everybody. It's 12 o'clock, so we'll go ahead and get started. Before we get started for today, I didn't post a sheet with all your test information over the weekend. I didn't get to that. I'll try and get that done today. Did anybody have any questions outside of stuff that I talked about last week? The test is written, it's 4 questions. It's kind of a combination between, ideas and problems. It's more or less based on the things we've been doing in class. For timing, a lot of people do tend, especially the first test of a course, a lot of people tend to say they feel like there's not enough time. So I wrote up a full set of solutions for the test this morning, and it took me about 12 and a half minutes to write the full set of solutions. Now, I have an edge. I've been doing physics for 30 years, and I wrote the test. I know what it's all about. But what that tells to me is that sheer writing time is about 12 or 15 minutes. Like, that's about how much time it'll take you to physically write things down. That sort of leaves you with about 35 minutes for thinking and trying again and stuff like that. So, for what it's worth on my end, I think it's a decently timed test, and I think it's fairly timed, but you might have to practice working quickly to get your ideas down, just to make sure you get it all done and you're happy with it. Okay, so let's get going with today. Last day we talked about Gauss's law. We said there's 2 ways to find Gauss's law. We do the scalar product between electric field and area. That's when we have simple situations. A general application of that is that you could do the integral of E over the area. We won't do those problems, but that is an expression. That's how you'd see Gauss's law in most books. You can also find net electric flux by taking the charge inside a closed Gaussian surface and divide it by epsilon naught. Whichever way you do it, you get the same answer. So that's what Gauss's law tells us. We talked about some properties of a conductor in electrostatic equilibrium. We said that the electric field was 0 inside the conductor, and if there was any excess charge, it had to sit on the surface. And the reason we started talking about the conductors is because we said we were going to apply Gauss's law to a conductor, and that's where we're going to start today. We're going to look at a spherical conductor, apply Gauss's law, and see what we figure out. Yep.
So will this stuff that we're covering today be on the midterm? Because
No.
we said that Gauss's law was where we were.
The cutoff was the end of last class.
Okay.
Yeah. This will be on the next midterm. So our task is, let's use Gauss's law. Let's find the electric field due to a spherical conductor with radius A, and it carries a net charge of Q. So this is our goal. This is what we're going to try and figure out. If we want to find the electric field, this means find the electric field inside and outside and write your final result in the end. To do our answer here, the first thing we're going to do is ask ourselves, what do we know about a conductor, and what is that going to tell us? What we know about a conductor, from our properties of a conductor, plus just the nature of a conductor itself, is that the charge is allowed to move. So any excess charge will spread to the surface of a conductor. So that's something we know about the nature of a conductor. So that means in a conductor, if it has an excess charge, or a net charge, or however you wish to describe it, all of those extra charges will sit right on the surface of the conductor. And we know that's true because that's how conductors work. So our next job is we're going to write Gauss's law, and that goes hand in hand with choosing a Gaussian surface. So when we write Gauss's law, and we have lots of symmetry here, we're going to use the simplified version. Net electric flux is found in one of 2 ways. The scalar product between the electric field and the area, or the net charge enclosed by the Gaussian surface divided by epsilon naught. So as soon as you write down Gauss's law, you're talking about a Gaussian surface. So your next step is to identify your Gaussian surface. So those 2 things should always be done at the same time. We'd like to find the net electric field both inside and outside the conductor. Let's do inside first. If we want the electric field inside the conductor, let's choose a Gaussian surface that's inside the conductor, because that's where we want to find the field. Okay, so number one, it's going to be inside the conductor. The second thing we'd like to do is to make this scalar product simple. We want to have the symmetry of the Gaussian surface to reflect the symmetry of the object. If we have a spherical charge, we should have a spherical Gaussian surface. Okay? If you try to do a box in here, then trying to take that scalar product would be really tangly, but a sphere is going to be a lot easier. So our Gaussian surface is going to be a sphere so that it matches the shape of our charge. And it's going to have a radius less than the radius of the charged conductor. So we identify it, then we draw it, typically with a dashed line, show the radius, and then we label it, this is the Gaussian surface. Okay, so there's our setup. So far, so good. Any questions? So now we get into using Gauss's law. So let's just write down Gauss's law again. So if we look at this, let's think about something we know. Let's think about this Q enclosed. Q enclosed means the net charge or the total charge enclosed by the Gaussian surface. If we look at our Gaussian surface, we'll ask how much charge is inside here. The answer to that question is 0. All of the charge is on the surface, none of it is inside, so Q enclosed has to be 0. So if Q enclosed is 0, then E dot A has to be 0, which means E has to be 0. And then I would argue this is a result we knew anyway. We know that the electric field inside the conductor is 0. But this takes us through the method of using Gauss's law to show how that's true. Okay, questions here? So when we do Gauss's law with spherical charges, this is the format we're going to follow. So we've done inside the conductor. Let's repeat the process and let's do outside the conductor. So we're going to do all the same steps, except we're going to look at outside instead of inside. So I cheated a little bit on my diagram and I already drew my pluses in, so there are all my charges sitting on the outside of the conductor. We'd like to find the electric field outside, so the first two things we'll do is we'll write down Gauss's law and we'll choose our Gaussian surface. Gauss's law says the net electric flux is E dot A equals Q enclosed divided by epsilon naught. So area A is the area of the Gaussian surface. Q enclosed is the charge enclosed by the Gaussian surface. That means we have to identify the Gaussian surface. We have a spherical charge, so we should choose a spherical Gaussian surface. We'd like to find the electric field outside, so our Gaussian surface should be outside the conductor. Okay, so that's where we're going with our Gaussian surface. I'm going to draw it. I'm going to label my R. And I'll label this as my Gaussian surface. So my Gaussian surface is a sphere. It has a radius r, which is greater than the radius of my conductor. Okay, so I've reflected the symmetry and I've put my surface at the place where I'd like to find my electric field. Are we good to hear? Okay, let's come back to our Gauss's law and see what we're going to do here. Gauss's law has two sides, E dot A and Q enclosed divided by epsilon naught. Let's sort out E dot A, then we'll sort out Q enclosed, then we'll put them together. So E dot A is the scalar product of the electric field with the area of the Gaussian surface. when we have a spherical charge, we know what the electric field looks like, and we can draw those electric field lines. They go straight out from the conducting sphere. Remember, when we use Gauss's law, we rely on the fact that we know a lot of these electric field lines. We know what they look like. So my electric field is radially outwards. My area vector is going to be radially outwards from the sphere. So if you drew the normal unit vector, that would point radially out. Your area vector is parallel to that, so that's radially outwards. So our area vector is also radially outwards. If those two things are radially outwards, it means they're parallel. So when we do Gauss's law, we need all this symmetry so that taking the scalar product is an easy thing to do. When we do a scalar product, we can do components or magnitude and angle. Let's do magnitude and angle for this one. So we've got the magnitude of the electric field times the magnitude of the area times the cosine of the angle between them, theta. Two vectors are parallel, theta equals 0 degrees, and cosine theta equals 1. Or cosine of 0 equals 1. There we go. So that leaves us with E times A. A means the area of our Gaussian surface. The Gaussian surface is a sphere, so we remember that the area of a sphere is 4 pi r squared. Okay, we're good with those steps? So that's the left-hand side of the equation. Next, we'll do the right-hand side of the equation. What is Q enclosed? So for Q enclosed, in general, what you have to do is look at the picture and just ask how much charge is inside the Gaussian surface. My Gaussian surface is this dotted line. If I ask what's inside it, I say the entire conductor is inside it. How much charge is on the conductor? That's charge Q. So the charge inside is all of the charge because the whole conductor is inside. Okay, so we found the left hand and the right hand sides of the equation. The next thing we'll do is we'll put those together to get to our answer. So Gauss's law says that our net electric flux is E dot A equals Q enclosed divided by epsilon naught. E dot A is E times 4 pi r squared. Q enclosed is that net charge Q, dividing that by epsilon naught. Solve for our electric field. E is 1 over 4 pi epsilon naught times Q over r squared, and the direction we already knew was radially out. And then if you preferred to include Coulomb's constant, you might recognize that 1 over 4 pi epsilon naught was Coulomb's constant K. So you could put that as KQ over r squared if you preferred. So the kind of interesting thing about this result is that the electric field inside the conductor is 0, and once you're outside, it looks just like a point charge. Same equation as point charge. Okay, so once you're outside, it doesn't care if it's a point charge or if it has an actual physical side. Questions? So the next thing we'll do is we'll make a graph of our result, because that's the sort of thing that we do. So the next thing we'd like to do is plot the electric field due to a spherical conductor with net charge Q and radius A. So we'll put the electric field on the vertical axis, we'll put the distance from the center on the horizontal axis, and we'll see what our field looks like. The interesting point, or one interesting point, is what happens when we hit A. So inside the conductor, we know the electric field is 0. So we just draw that as a horizontal line, and then if we wish, we can write on our graph, this is for inside, for R less than A. When we get to R equals A, the electric field is going to jump to K times Q divided by R squared, but R is equal to A, so it'll be K times Q divided by A squared. So that'll be a point on our graph. And then electric field falls off as 1 over R squared. So this line will fall away as 1 over R squared. That's a curve, looks something like this. So E falls off as 1 over R squared. What that means is if R equals big, E gets very small, and as R gets to infinity, the electric field will get to 0. Sometimes we connect these two by a dashed line, or you can just leave it as a jump. And this value up here then, since it's 0 before, falls away as 1 over R squared after. This is the maximum value of the electric field. And this bit is for it. Okay, questions? Okay, so that's the electric field inside and outside of a spherical conductor. Yeah,
What if R was equal to A?
that's what happens right here. When R is equal to A, the electric field is KQ over A squared. That's where it kind of transitions. Yeah.
So that means it touches the surface of the conductor?
Yeah, that's kind of an interesting question. If you approach the conductor, the surface from the inside, the electric field is 0. If you approach from the outside, the electric field is KQ over A squared. Sort of right there at the threshold of the surface, whatever that means. That's what it's equal to. Yeah, that's an interesting sort of math thing. Okay, so we've got the process down. Let's see if we can move through the process a little bit more quickly, and let's do the insulator. So for our insulator, we've got the same question, same diagram. Our insulator has charge Q, but an insulator is different, and it says that the charge is uniformly distributed throughout its volume. So if we ask, what is the nature of an insulator? How is it different from a conductor? We know that in an insulator, the charges don't move. They stay where they are put. Okay, so charges don't move. So if our charges begin uniformly distributed, they will stay uniformly distributed all the time. So as a sketch, I will just put in a bunch of pluses for positive charges. And it's kind of uniformly distributed. That's the best I can do in a sketch. Okay, so those are an even density everywhere. So if we want to find the electric field inside and outside, we'll start with inside. We want to write Gauss's law, choose a Gaussian surface. Same deal as with the conductor. Gauss's law is that the net electric flux is E dot A equals Q enclosed divided by epsilon naught. We want to choose a Gaussian surface. If we want the electric field inside the insulator, we'll pick our Gaussian surface inside the insulator. We'll label R for the radius, and we'll label it as our Gaussian surface. So our Gaussian surface is a sphere. with radius r less than the radius of the insulator. Okay, so far our setup is the same. We have to do our two bits, the left side and the right side. Let's think about the left side first. Our electric field, due to the positive charge inside the Gaussian surface, is going to point radially outwards. So there's our net electric field. Our area vector also points radially outwards. So the normal unit vector points radially out. There's N. The area unit vector is parallel to that, radially out. So now we can deal with the left-hand side of Gauss's law. So E dot A, E points out, A points out. These are parallel just like last time. Equals E times A times cosine theta, but theta is equal to 0. Cos 0 is equal to 1. A is 4 pi r squared. E times 4 pi r squared. Okay, I did this one really fast because it's the same as what we did before. Now we have to deal with the left-hand side of the equation and ask what is Q enclosed. This is the one that's going to get a little bit tangled. So for Q enclosed, let's first of all remember, what do we mean by Q enclosed? Q enclosed is the charge enclosed by the Gaussian surface. So here's the key part to this problem. Our Gaussian surface is right here. The charge are all those plus signs that I've drawn. Is the charge enclosed by the Gaussian surface less than Q, equal to Q, or bigger than Q? What do we think?
Less than Q.
Less than Q. So our Gaussian surface only encloses part of the sphere, so it only encloses part of the charge. So we know that Q enclosed is less than Q. Okay? It's only got part of the sphere, so it's only got part of the charge. Well, what is Q enclosed? If you want to figure out what the charge is, let's use an analogy to mass. If you had a hunk of aluminum on your desk and you knew what volume it had, you could use the idea of density to figure out its mass. You know, mass is density times volume. If you had 2 cubic meters of aluminum, multiply by the density, and you know what the mass is. We can apply the same deal to charge. So what we'll do is we'll say that our Q enclosed is the charge density times the volume of the Gaussian surface. So rho is what's called volume charge density. So a hunk of aluminum would have a mass equal to the density times the volume. This bit of insulator has a charge equal to the density times the volume. The volume of the Gaussian surface, that gets easy, that's just geometry. The density is a little bit trickier, but it's not too bad. The density is total charge divided by total volume. Okay? So density means charge density, volume charge density, so it's charge divided by volume. So the total charge on the insulator is Q, the total volume of the insulator is 4/3 times pi times AQ. Okay. So now we've dealt with the trickiest part of this problem. Let's keep going and we'll get to our answer. So the amount of charge enclosed by that Gaussian surface is rho times the volume of the Gaussian surface. Rho is our charge density, charge divided by volume. The volume of the Gaussian surface is 4/3 pi r cubed. Our 4/3 cancels and our pi cancels, yep.
Actually,
So 4/3 cancels, pi cancels. And this volume charge density, this is a constant value because it's uniformly distributed. If you'd like to have hard problems where the volume charge density is not uniform, you can go ahead and check out Physics 2055. That's where they do the more challenging problems. So we're left with Q times R cubed divided by A cubed. So this is the fraction of charge enclosed by that Gaussian surface. Now we're going to put everything back together. So we'll get our Gauss's law, we'll fill in the E dot A part, we'll fill in the Q enclosed bit, and then we'll figure it all out. So back to Gauss's law, net electric flux is E dot A equals Q enclosed divided by epsilon naught. E dot A is E times 4 pi r squared. Q enclosed is Q times R cubed over A cubed, and that's divided by epsilon naught. We'll solve that for E. E is equal to 1 over 4 pi epsilon naught. Got R cubed here and R squared here, so I can divide both sides by R squared. I've got Q over A cubed times R, and the direction is outward. So my electric field inside the insulator is different from the conductor. That makes sense because there's charge on the inside of the insulator where it's not on the conductor. And we see that it's proportional to the distance from the center, so it's linear with respect to R. So we see that E is proportional to R. Okay, questions there? So that's for inside the insulator. Next, we want to get outside the insulator. And I think we can get through that one really quickly. Okay, so now let's go for outside of our insulator. We're going to follow all of our same steps that we've done 3 times now. So we'll write down Gauss's law. Net electric flux is E dot A equals Q enclosed divided by epsilon naught. We'd like to choose a Gaussian surface. I know that my charge is uniformly distributed throughout. I know that I'd like to find my electric field outside, so I'm going to choose my Gaussian surface to be a sphere with a radius bigger than the radius of my insulator. My Gaussian surface, sphere with R greater than. Now I'm going to figure out my 2 bits of Gauss's law. The first bit, E dot A. I'm going to write, just because we've done this little bit of math twice already, I'll say show steps equals E times 4 pi r squared. Then the other bit of Gauss's law we need is what is Q enclosed. Q enclosed here. There does tend to be one pitfall here. I think people just kind of get into overdrive and they get stuck into equation mode in a test. So one pitfall I have seen in the past is that people want to find the charge inside the Gaussian surface and they apply this equation again, Q times R cubed over A cubed. That's tricky, right? If R is bigger than A, right, if we're outside, this R is bigger than A, that means Q enclosed would be bigger than the total charge. And I think if you think about that, that doesn't make any sense. Where would that extra charge come from? But when you're in a test and you're just scribbling equations as fast as you can go, it can be easy to slip into things like that. So make sure you're thinking as you're writing. If we ask our question, Q enclosed means the net charge enclosed by the Gaussian surface. What's inside the Gaussian surface? The insulator is inside the Gaussian surface. Therefore, the net charge is the net charge on the insulator. It's just Q. Okay, so that thought process should help you get your charge right every time. So it's whatever is inside the Gaussian surface. That's where the charge comes from. We'll put our two bits together. We'll solve for E. And we know the direction is radially out. Okay, and again, if you prefer to write Coulomb's constant instead of 1 over 4 pi epsilon naught, that's fine too. What you might notice about this result is that it's exactly the same as the conductor, and it's exactly the same as the point charge. So once you're outside your charged object, Gauss's law doesn't care about what it was, the physical nature of it, so it looks exactly the same. So like point charge and conductor. Okay, good to hear. Okay, and just like we made a graph of the electric field for a conductor, we'll do a graph of the electric field for the insulator. So graph the electric field for a spherical insulator. It's got charge Q uniformly distributed throughout its volume. It's got radius A. I've written down the two results that we just found on the last two slides, and we'd like to make a plot of this. So when we're inside the insulator, E is proportional to R. It increases linearly. So this is inside. When we get outside, it falls off as 1 over R squared, just like the conductor did. So it's got the same shape. And E falls off to 0 as the distance from the sphere gets very large. So then our interesting point we'd like to label is what happens at R equals A. There, our electric field will be 1 over 4 pi epsilon naught times Q over A squared, which will be our maximum electric field. Yeah.
How is the first part linear if the area is R squared, not just R?
So this part right here.
Yeah.
So remember, the area was on the left-hand side. So the area was on the left-hand side of the equation, 4 pi R squared. On the right-hand side, our Q enclosed depended on R cubed. It depended on the volume. So when we got here with our Gauss's law, we had R squared here, divided into R cubed here, and that left us with just an R in our expression for our electric field. So basically the R squareds cancel. Okay, questions? The next slide in the notes, if you have a look at them, is the same problem again, except I just put numbers with it. So you go through the same process, plug the numbers in, and just get numerical answers. So I will post the solutions to that. And we'll do a different example here in class. So in this example, a thin-walled hollow sphere. So let's just draw a picture of this to get started. So a thin-walled hollow sphere, you might picture something like a bowling ball. of radius 0.250 meters. Has an unknown charge distributed uniformly over its outer surface. So the charge, whatever it is just uniform over the whole surface. At a distance of 0.30 meters from the center of the sphere, the electric field points radially inwards and is 1.8 times 10 to the minus 2 newtons per coulomb. Okay, so anywhere that far away, the electric field is pointing inwards. So here's what our electric field lines look like. What is the charge on the sphere? So right off the bat, before we get started, the electric field lines point inwards. Does that tell you the sign of the charge? That's got to be negative, right? So we anticipate a negative charge. Let's make sure that the math is going to back that up, but we think this charge is going to be negative because the electric field points inwards, right? We know it's out of positive and into negative. So what we know is that our electric field at 0.300 meters is equal to 1.80 times 10 to the 2 newtons per coulomb, and the direction is radially inward, which we have drawn. So let's think about our Gauss's law. E dot A is Q enclosed divided by epsilon naught. This is the charge enclosed by a Gaussian surface, electric field dotted with the area of a Gaussian surface. This means we need to identify a Gaussian surface. We know the electric field at 0.3 meters from the center. So to me, this says we should draw a Gaussian surface, which is a sphere with a radius of 0.3 meters, because that's where we know the field. So here's my Gaussian surface. I'm going to call that R. The Gaussian surface its sphere R equals 0.300 meters. So we pick a Gaussian surface in a shape that's useful, spherical, and at a position that's useful where we know the electric field. We know from our previous math that E dot A equals E times A times cosine theta. Let's figure out that theta. Every time you should go through it and figure it out. We know that a Gaussian, or the area of our sphere, is radially outwards from the sphere. So there's our area vector. I didn't draw my electric field all that well. Sorry, that's bad drawing on my part. So our electric field vector points in. Our area vector points out. Those two vectors are what we call anti-parallel. Some people like the word opposite better. If one is in and the other is out, that makes the angle between them 180 degrees. So that's E times A times cosine 180 degrees. That's -1. And A is 4 pi r squared. So I've got minus E times 4 pi r squared. So that's one side of Gauss's law. The other side, Q enclosed, that's the bit we're trying to figure out. So let's put our equation together. So E dot A equals Q enclosed over epsilon naught. E dot A is minus E times 4 pi r squared equals Q enclosed over epsilon naught. Q enclosed equals minus epsilon naught times E times 4 pi r squared equals minus 8.85 times 10 to the minus 12 coulomb squared over newtons meter squared times E, that was 1.80 times 10 to the 2 newtons per coulomb times 4 times pi times 0.30 meters squared. Rats, I ran out of room. So sorry. So the charge, when we do that on the calculator, is minus 1.80 times 10 to the minus 9 coulombs. So when we do the math, we get the negative charge, and that makes sense with our expectation because the electric field pointed inwards. Yep.
Would you need to state that you know that since the Gaussian sphere that you made encloses all of the charge, that is why we know that that charge is equal to the charge on the entire sphere? Because the question's asking what's the charge on the entire sphere? not
Right.
the Enclosed.
It would never hurt to have that statement. On a test, I'm not sure I'd ding you for it because all the charge is inside.
Yeah.
Yeah. Yeah, so it wouldn't hurt, but I don't think you have to. Yep.
Does hollow mean like it's an insulator?
Pardon?
Does hollow sphere means it is an insulator?
Oh, that's such a good question. The problem doesn't really say if it's an insulator or a conductor. We don't know. Yeah.
So it will be wrong if we like subtracted both radiuses, like 4 pi r squared, negative 4 pi r squared.
Yeah, that's the bit about the thin. So it means that kind of the inner radius is about the same as the outer radius. And it only gives you one radius. It's just 0.25. That's because it's very, very thin. Yeah. You could have one that's solid, but it would be a slightly different problem. Yeah. And then you would need to know if it was a conductor or an insulator, because we know the electric field inside a conductor is 0, but not the insulator. Yeah, good questions. Okay, so those are our examples of Gauss's law with spheres. Now let's go back to our properties of a conductor. So in our properties of a conductor, we showed number 1 and number 2 were true already, so that the net electric field inside a conductor was 0. We showed that any excess charge had to be on the surface of a conductor. That's because the field inside is 0 and all the charges repel. Now we're going to come to number 3, where it says that the electric field just outside a conductor is perpendicular to the conductor, or perpendicular to the surface. And the magnitude of the electric field is the surface area charge density sigma divided by epsilon naught. So this sigma is our area charge density. That's the charge divided by the area. So we're going to go ahead and look at property number 3 now. And this was a result that we spoke about when we did the planes of charge. We gave this result and said it was true. And then we went ahead and we used it to make a capacitor. So we're coming back to that idea now. Okay, so what is the electric field magnitude and direction outside the surface of a conductor? The surface charge density sigma is Q divided by A. I'd like to start with the idea of the direction of the electric field first. So I'm just going to draw a new sketch down here. Here's my conductor. I've got some sort of generic curved surface. And on the surface of my conductor, I have a charge because I know that the excess charge on a conductor sits on the surface. Let's say, first, I'm going to assume a generic result that my electric field is at some angle. Okay, so that's just going to be the generic result I'm going to assume, that the electric field at the surface of my conductor is partly up and partly right. Electric fields are vectors, so it has components. So one component of that electric field would point to the right. I'm going to call that the bit that's parallel to the surface. And one component of the electric field points straight out. That's the bit that's perpendicular to the surface. You okay with this bit? So I've assumed it's at an angle. It's got two bits, a parallel bit and a perpendicular bit. Let's think about those two bits and the fact that we're talking about a conductor in electrostatic equilibrium. So we're still in electrostatic equilibrium here. So our conductor is electrostatic equilibrium. If it's an electrostatic equilibrium, these charges are not moving left and right on the surface. They're staying put. So they're on the surface and they are not moving left or right. That means the parallel component of the acceleration is equal to 0, okay, because it's in equilibrium. If the acceleration is 0, the parallel component of the force has to be 0, because force is mass times acceleration, which means that the parallel component of the electric field, which is the force divided by charge, is also equal to 0. Okay, so that parallel component must be 0. Otherwise, the charges would move left and right, back and forth on the surface, and they don't move because that's our condition, is that they're not moving. So the direction of the electric field is perpendicular to the surface. So that's half of the result. The other result is finding the magnitude. To find the magnitude, we want to use Gauss's law. So let's start trying to apply Gauss's law. To apply Gauss's law, we need to have a Gaussian surface. So I'm going to pick a Gaussian surface. And I want to pick strategically. I'd like to find my electric field outside the surface of the conductor. So I certainly want at least part of my Gaussian surface to be outside the conductor. I'd like to incorporate the fact that I know the electric field inside a conductor is 0. So that leads me to pick a Gaussian surface that's going to be a little cylinder, and part of it is going to be outside the surface, and part of it is going to be inside the surface, and it's going to be perpendicular to the surface. Okay, so that's what I'm going to pick because it lets me figure out what I want to figure out. So there's my Gaussian surface. So it's partly in and partly out. The face has area A, and it's perpendicular to the surface. Okay, so there's the details of my Gaussian surface. On top of this, I'm going to draw my electric field vectors, because I know my Gauss's law needs to know the direction of the electric field. I settled the direction of my electric field vectors, which is perpendicular outward from the surface. So there's the direction of my electric field. Okay, are we good to here? Oh no. Okay, so our time is actually pretty much up. So I hate to stop right in the middle, but I think we have to stop here. We'll finish this up on Wednesday, and then our test is on Friday. Today is my day I'm running to my other class, so I can't stick around for questions, but I'll be in for my office hours this afternoon if you want to come by.
What time are your
3 to 4.